It's hard to grasp what an LLM is without having at least some general idea of its overall skeleton. We're going to explore their structure at a high level. The main premise of language modeling is predicting the next word or subword, called tokens, based on the text observed so far. The transformer-based architecture is the foundation of large language models and consists of several key components that enable these models to process sequences and generate human-like text. There are several components in the transformer architecture. First are the input embeddings. The tokens entered by users are referred to as inputs. Tokens can be thought of as equivalent to individual words in text, though in reality, it's how LLMs break up sequences of text into subunits, sometimes words, and sometimes random chunks of characters. Since models can only understand numerical data and not raw text, these inputs are converted into their numerical representations known as input embeddings. This conversion allows the model to process and understand the text effectively. Next is positional encoding. This technique is used to encode the position of each word in the input sentence as a set of numbers. Positional encoding is crucial because it preserves the order of words, which is essential for maintaining the meaning of a sentence. Without this, the model would not be able to understand the context of your prompt properly. This property of LLMs is very relatable to normal human communication. The encoder is a part of the neural network that processes input text and generates a series of hidden states. Very simply, these hidden states capture the meaning and context of the text, allowing the model to comprehend and generate relevant responses. They're considered hidden as they're not directly observable from the input or output data. The encoder works by applying multiple layers of attention and normalization mechanisms to refine the input embeddings and extract meaningful patterns statistically. The decoder is a critical part of the neural network that generates the output sequence based on the encoded input sequence. When an LLM is training, the decoder learns to predict the next word by analyzing the words that come before it. This process allows the model to generate coherent and contextually relevant text. To enable the decoder to guess the next word, the output sequence is shifted one spot to the right. This way, the decoder can only use the previous word to predict the next token. This step is crucial for maintaining the logical flow and structure of the generated text. Similar to input embeddings, the output is then converted into a numerical format called output embeddings. These embeddings undergo positional encoding to understand the sequence of words. During training, a loss function is used to compare the model's predictions with the actual target values. The parameters of the decoder are then updated based on this comparison to improve accuracy. Finally, the linear layer maps the decoder output embeddings to a higher dimensional space that matches the input space. Then, the softmax function then generates a probability distribution for each output token, determining the most likely next word in the sequence. Not all language models require an encoder and a decoder. Gemini uses an encoder-decoder architecture. Overall, transformers are designed to efficiently process and understand input from long sequences, making them highly effective for natural language processing tasks. This means transformers excel at handling sequential data, such as text. Further, this architecture allows LLMs to gather context from the extensive amounts of input data, enabling them to generate coherent and contextually relevant responses. However, LLMs aren't just restricted to text. As we'll soon see with Gemini, it can take in all sorts of data, such as images, videos, and audio.